And this is lecture 14 for our class on real-time digital signal processing for the spring 2014 semester. So this is lecture 14, part 2. We'll talk about match filtering. We'll derive it. It's a long derivation, but some good stuff along the way. So last time we covered transmitting 1 bit at a time and a little bit about 2 PM systems, transmitter receiver. Today's match filtering for part 2, and then we'll have a part 3 and 4 for the remainder of this, intersymbol interference, closed form formulas for probability of bit error given SNR, and eye diagrams. All right, so let's move on to part 2. So part 2 left off here on part 1, which was the match filter. And really, this is a more general story. It's not just communication systems. We use match filtering in lots of scenarios: ultrasound, sonar, radar. Very common technique. And the idea is to detect a pulse that we know embedded in noise. Very common problem in detection. And again, yes, there's a communication system application. So again, so for our match filter, we're going to detect a pulse in the presence of additive noise. And the receiver is going to know what it's looking for. We're going to ignore the channel memory for the purpose of the derivation, so we'll assume that either it is negligible or it's compensated by other means. For example, a channel equalizer in the receiver. So our setup is as follows. We have a pulse shape that we know that the transmitter is sending out. That's G of t. It is being distorted or degraded, really, is the better phrase here, by additive noise. The additive noise follows a Gaussian distribution. It's spectrally flat, so the power spectrum is a constant, and that constant value for the power spectrum is equal to the variance. The historical name, again, is white Gaussian noise. I prefer spectrally flat. I'll use both. And the mean is 0, so we assume that the average value is 0. Now, this is over a long observation. So if you observe this noise for all time from minus infinity to infinity, the average value is 0. But it's possible in shorter intervals of measurement, you may see a DC value. This is the on average over all time. So the channel here really just has this only source of degradation is the additive noise. So again, our transmitter sends out a known pulse. The channel, the only degradation that we're considering is additive noise. And then the receiver, at least the part of the receiver that's going to detect the pulse, is the match filter, and then we sample at some regular interval. So in this regular interval for the communication system example will be the symbol period. So the sampling time can vary with application. For our application, it's the symbol period that we're interested in. We want to try to detect a particular amplitude. We want to set up a good estimate of the symbol amplitude that had been used in the transmitter. And that estimate of the symbol amplitude resides here. So this is the estimate of the symbol amplitude. Per symbol period. Go ahead.
Sorry, this is
okay.
What is special about the match filter?
What is so special about the match filter? We will derive that today. What is so special about the match filter, if you design it right, you maximize the signal-to-noise ratio at the output of the sampling block. Okay. Now, why is so that's important for a couple of reasons. One is that the detection probability is going to vary with SNR. So the higher the SNR, the more likely you're going to correctly detect the pulse in the noise.
We designed that knowing what sort of noise.
Correct. You design the match filter knowing the shape of the pulse signal being used, the pulse shape, and duration. Right, so this assumes knowledge of the pulse shape being used. So the match filter will have the same frequency selectivity as the pulse shape. And we've seen the formula already from the end of part 1. So the best we can do for the match filter, the optimal choice for the impulse response, completely depends on the pulse shape. All right, so it's some gain times the pulse shape conjugated, but our pulse shapes have all been real valued, so there's not a lot of work the conjugation has to do for this case. I take the pulse shape, I flip it in time, and I delay it by the symbol time. Now that's the best I can do. If I'm a little bit off, it's not a big deal. All right, so we're going to spend a lot of time deriving this thing, and if it's a little bit off, we're still going to get pretty good detection. All right, but at least let's find what the best that we can do, and that bound's very useful in looking at the impact of other things in the receiver, like using a different pulse shape, using a particular equalizer, using a particular symbol recovery algorithm. So let's at least find a bound that we know that's possible to reach in theory, and let's see how far we can, how closely we can get to that bound in an actual implementation. All right, so that's the best we can do. All right, so let's keep going with the setup here. So a pulse shape G of t, this is deterministic, it's known. It's a rectangular pulse. It's a truncated sinc, truncated raised cosine. It's a triangular, whatever it is. It's some pulse shape that we know, and it's deterministic. It's fixed. What's random is the additive noise. That's the source of our randomness and uncertainty. The match filter, in the end, will be deterministically defined. It will be defined completely in terms of the pulse shape. And it's also flexible in that we allow a gain. Any gain will do. This is good for automatic gain control and other reasons in the receiver. So it's another degree of freedom that we can exploit in the design of the full receiver. Okay, so if we look at what's going on here from just how signals are flowing through the block diagram, I've got the receiver is getting two inputs, right? It's seeing the pulse shape, G of t, and the noise, W of t. So Y of t, the output of the match filter, has two components. I have the convolution of the pulse shape and the match filter's impulse response, and the second input, I have the additive noise in the channel convolved with the impulse response of the match filter. And I'm going to just combine those, just placeholders. So I'm going to have G naught of t be the part that I want. This is the pulse that gets through the match filter, and that's what I'd like to have the most power in. I'd like to have the most signal power I can getting through the match filter, and more than that, I really want it to get it all the way through to Y of t. And so this is our point of interest. We'd like to maximize some measure of signal quality. We're going to go after signal to noise ratio. The second part of this Y of t is simply the filtered noise. If the pulse shape is low pass, then the match filter will be low pass, which is the case that we deal with for our communication system application. Pulse signal could be lots of other things. It could be a chirp, which is a cosine of increasing or decreasing frequency with time. That's common in sonar. So, but we know what the pulse shape is, what we're looking for. All right, so our job here then at the sampled value of Y of t, this Y of capital T, which is really, I'm giving you one symbol, the sample at the end of the first symbol, but it's going to be holding for all the remaining symbols, is that I want to really get the most power I can. I want to maximize the power here, and I want to minimize the power here. So maximize the power of G naught of t after the sampling block, and minimize the noise power. So I want to maximize the signal power and minimize the noise power. Okay. Well, you want to let the receiver, so the question is why wait until the end of the symbol period to sample? And really it's just a matter of getting a good estimate. Right, so really we basically want to look at what happens over a symbol period, and at the end of that symbol period, after we do the best we can lifting the pulse out of the noise, then we take a sample. We're going to keep doing this. We're going to take it. We're going to take the value at, again, capital T is a symbol period T sim. We're going to sample at T sim, 2 T sim, 3 T sim, and keep going. All right, so there's a, so you could, I mean, I suppose you could decide to put in throw out the first, so many seconds of stuff of received signal and then start sampling every symbol period to account for group delay of the channel. But remember, and that would be fine. In this particular example, there is no channel impulse response. There's no channel filter. But if there had been an FIR filter in the channel, then the receiver, we would first throw out that many seconds of received signal corresponding to the delay through the channel filter. And then we go about, right? So again, the only source of degradation in the channel is additive noise. If there are other sources of degradation, will be other subsystems in the receiver that will compensate for those. So if there's channel memory, in other words, there's an FIR filter in our channel model, then we'll have an equalizer in the receiver. And the equalizer will actually let us know what that transmission delay is, and then we can just throw it out. That's homework 7. It's coming pretty soon. All right, so this is the setup, and so the derivation is going to be pretty long, but some good stuff along the way. We'll do autocorrelation in a little more detail, and power spectra and stuff. All right. Any more questions? This is the setup, though. This is a pretty important slide. It sets up the whole lecture. Okay, maximize signal power, minimize noise power, which is another way of maximizing the signal-to-noise ratio, which we'll see on the next slide. Okay, again, so the design of the match filter, we have a couple goals here that are simultaneous. We want to maximize the signal power. That's the power of G naught at the sample, T equals T sim, at the end of the symbol time. And we're going to minimize the noise power. And we're going to go after, so we have to figure out a measure of both the signal power and the noise power and put that together into a signal-to-noise ratio. And there are many choices here. The particular type of SNR we're going to go after does the following. So we're going to combine these two design criteria to come up with a single SNR measurement. And it's called peak pulse SNR, and honestly I forgot why it's called that offhand. But so the ratio here will be some measure of signal power. And we're going to go after instantaneous power after sampling. So this is the power of the signal, the pulse signal, that gets all the way through here. Okay, so that's the instantaneous power of the signal. At this y sampled at little t equals capital T. And then for the noise, we're going to go after the average power. Okay, so again, noise is it's a random process, which means at any point in time, little t, the noise process takes a value from the Gaussian distribution, zero mean, and a fixed variance. The variance is constant for this derivation. It doesn't change with time. And so the average power here, so think about what is power. Well, power is going to be, the instantaneous power is the value of, is proportional to n squared of t. So at any point in time, this is a voltage, n of t is a voltage, the power is proportional to the voltage squared. But since it's a random number, what we really want is what's the average power over all time, and that's where the expectation comes in. So this is really the expected value with respect to little t of the noise process squared. In other words, it's the expected value of the instantaneous power of the noise. And again, expectation simply means average what's ever inside over the duration of observation. Now, in homework problem set number 4, you dealt with expectation quite a bit over finite observation. So today we'll do some of that over infinite amounts of time. In practice, we'll do everything over finite observations, but it's nice to have the bound here. So again, the average power is the average noise power averaged over all time. Okay, so if we maximize the signal-to-noise ratio as defined here, we will simultaneously maximize the instantaneous power of the signal and minimize the average power of the noise at the same time. Go ahead.
Why don't we take the absolute value for the noise power?
Well, the noise power is assumed to be real valued. The noise signal, sorry, the random process NFT is assumed to be real valued. If NFT were complex valued in our model, then we would need to do absolute value squared. That's right. Here we don't need that. Okay. All right, now let's take a tangent for a couple of slides on power spectra and autocorrelation, and we'll come back to applying it to the SNR formula. So for power spectra, we have a pretty good idea how to do that for deterministic signals. We've been doing it, I think, since homework 1, early in the semester. So if we have a deterministic signal x of t, and it's got a Fourier transform capital X of f, and the same thing would hold in discrete time. The power spectrum is the square of the absolute value of the magnitude response. We're going to ignore the phase. So what we've been doing, and this is what really plot spec does this, except it just does the absolute value, does the magnitude. If we want the power spectrum, then what we want is the absolute value of the Fourier transform squared. This gives us a plot in the Fourier domain of the magnitude squared. So if my magnitude response were an idealized, right, so if that's my magnitude response, right, then my power spectrum is simply the same shape squared, so this goes to 4. So we have a pretty idea. We've been doing this for a while, looking at power bandwidth all the way back to lecture 1. We talked about bandwidth and estimating bandwidth. We've done it on homework all the way back to homework 1. So this we have a pretty good idea on because we have a lot of our signals generally have a Fourier transform. There are a few that don't, but we haven't really dealt much with those. So the signals we've been dealing with have Fourier transforms. You want the power spectrum, just take the magnitude response squared, and you're good to go. Now another way to calculate this is to take the Fourier transform and multiply it by its conjugate. If you remember, if we think about this in polar form, so if you let x of f be equal to the magnitude times a phase term, then if I multiply by the conjugate, then the phases are going to subtract out in the magnitudes square. So this is just this product of x of f, capital X of f times its conjugate is just another way of saying I want the absolute value of x of f squared. And that's important because we're going to use this other definition of the Fourier transform times its conjugate to derive a more general approach to finding the power spectrum using autocorrelation. And this more general approach will apply both to deterministic signals and to random signals. Kind of nice. One definition for both. All right, now a few Fourier transform properties. One we sort of use a lot, which is if I multiply in the Fourier domain, I can involve in the time domain. That we're pretty comfortable with by now. But the other one here I always have to look up. So if you get a Fourier transform table out, conjugation in the Fourier domain is time reversal and conjugation in the time domain. I don't remember this one. Got to look it up. So what does that mean? If I look at this definition of capital X of f times its conjugate, it's really, if I break down this product using Fourier transform properties, what it really is the inverse Fourier transform of capital X of f, which is, I'll get little x of tau here. So product in the Fourier domain is convolution in the time domain. I'm going to convolve the inverse Fourier transform of capital X of f, which is little x of tau, and the inverse Fourier transform of capital X conjugate of f. And again, from Fourier transform properties, that gives me little x conjugated and flipped in time. Okay? And so again, so another way to compute the power spectrum is to take the Fourier transform of a signal in the time domain convolved with a conjugated and flipped version of itself. Okay, so what's inside the curly braces for the Fourier transform is the autocorrelation function. Okay, so the autocorrelation function of x of t, we'll call this capital R sub x of tau, is just the x of t. We'll replace the little t with capital tau. So it's the little x of t convolved with the flipped version of itself. And then we have to conjugate the flipped version. For us, that doesn't do much. Our signals have generally been real valued. But in the case that x of t is complex valued, conjugation has a role to play. So a couple observations about correlation, and you encountered this in Lab 4 with PN sequences, pseudo-noise sequences, and on homework 4 with PN sequences. So the maximum value of this autocorrelation, when it exists, you've got to remember, it's kind of strange, but it's always nice to caveat, just in case there's some weird x of tau that is, bizarre to work with. So the maximum value when it exists, and also that sometimes the maximum value is tough, and when x of tau is a Dirac delta, the maximum value is hard to deal with, as you might guess. It's another reason it's up here. So the maximum value here when it exists is at the origin, and a property of the autocorrelation is that it's even symmetric. So and we'll use this on the next slide to our advantage. So the autocorrelation is even symmetric. Simply means that if I flip, in the time domain with respect to the horizontal or y-axis, or the vertical axis, then I get the same thing back. Go ahead. Correct. So the key is that if we got it, so this is the autocorrelation. The next step is cross correlation, right? Which is what we'll ultimately do. Right? So the match filter does autocorrelation. Is the autocorrelation? Well, we'll get the match filter from the autocorrelation function. It's coming. Okay. In practice, that match filter is cross-correlating against the received signal, looking for the pulse, like you did looking for a header in a sequence of received values in homework 4. There's an example. So if I let little x of t be a rectangular pulse, causal of length capital T sub s, amplitude 1, then the autocorrelation here is just the convolution of x of t with a flipped and conjugated version. So it's all back to convolution, which means it's all back to filtering. Yeah. Not a surprise in this class. So the autocorrelation gives us a triangular pulse. We're convolving two rectangular pulses, both of length capital T sub s. So the convolution result should be the sum of the two lengths. And so I get x of t, and I'm convolving x of t with x of the flipped version of x. All right, so I'm convolving x of t. I've changed, x of tau. I'll go back to t is fine. So I'm convolving x of t with the flipped and conjugated version of itself. So I'm convolving x of t with its conjugated and flipped version of itself. And if I don't have any shift, I want to shift left to right. Let me get this back. Didn't do it right. This is right. So I'm convolving these two signals. So to convolve, I'm going to take x star of t and flip it and slide it. So I'm going to flip it back in convolution and slide it. So when I flip it, when I flip x star the first time, x star of t the first time, I get back where I started. So now I'm going to be, so if I flip x of minus t and slide it, so I just flip it, I get complete overlap in my convolution. And that's my maximum value. And as I slide it left to right, I get the partial overlap, as I see here with the triangular result. So again, the maximum value is going to occur in the autocorrelation function at 0. Simply due that I'm, in my autocorrelation, I'm flipping x, and then convolution flips it back. In other words, what correlation does is it slides one function against another without flipping. That's correlation. Go ahead. For autocorrelation, you're going to get a peak at 0. For cross correlation, that's why you look for peaks. So you know that when you receive a pulse shape plus a bunch of noise, or a header and a bunch of random bits, and you slide the header across the received signal, you'll get a peak when the header you're looking for lines up with the header actually in the received signal. You'll get a peak. Go ahead.
The reason why we use cross correlation is because they're basically different sequences because of the noise.
Correct. And any other form of right. So the receiver is going to see the pulse shape plus noise, plus possible signal distortion due to memory. Right. That's what you saw in homework 4, problems 2 and 3. So you want to get a pretty. You want to pick a signal that can get through a pretty aggressive channel that has memory and additive noise. And so we saw the pseudo noise sequence does a really good job getting through such a channel. For autocorrelation, though, we always get our peak here at the origin, if there is a peak. Right. And you get decay. So all right. So this is for two deterministic signals, or for a deterministic signal, rectangular pulse in this case. But this type of autocorrelation applies just as well for random signals, which you'll see on the next slide. The same definition applies to both cases. Now, what's the autocorrelation if x of t is a Dirac delta? Just be a Dirac delta located where? At the origin. Okay. Let me ask you another question. What if I gave you x of t? So I gave you another x of t, but I delayed the start of x of t. Let me get a place to put this. What if I gave you this x of t? What's the autocorrelation function look like? Same thing. It's the same thing. I get a triangular pulse centered at the origin. Exactly the same answer. Which means that delay, this notion of autocorrelation is insensitive to delay. And if you think about it, it sort of makes sense because any delay in the time domain corresponds to a phase shift in the frequency domain, and we've gotten rid of the phase. We're looking at the magnitude squared. Phase is gone. So it kind of makes sense. We're not tracking phase. We're only tracking magnitude. Okay, we're good. All right. Right. Now let's apply this to a random signal, this idea of power spectrum. with infinite observations, from minus infinity to infinity. If it's finite observation, life is so much easier. That's 3 lines of MATLAB code, you know, down the bottom. It's easy. But for the infinite duration case, it's a little bit more involved. Because for the finite duration case, we can do the same thing for deterministic or random signals. It doesn't matter. The problem with the infinite length case, or the infinite observation case, is that a Gaussian random, or a random signal may not have a Fourier transform, but it has a power spectrum. And that's why we have to go through all this extra effort. All right, so again, we have a two-sided random signal, so we're going to be observing. This means that we look at t from minus infinity to infinity. This is theory. The power spectrum, as we said on the previous slide, is just the Fourier transform of the autocorrelation of that signal. Now let's see if we can get at it from, see if we can show that now for a random signal. Again, so for a two-sided random signal, the Fourier transform may not exist, but the power spectrum does. So let's see how we can get there. So we come up with another definition. Well, it's a definition that we use that will reduce to what we have on the previous slide. So if I take the autocorrelation and I define it as the expected value of the noise signal in a conjugated and shifted version of the same signal, then what does that mean? The expected value is simply some sort of averaging effect over all time. So again, this is with respect to little t, of whatever's in the curly braces. So what's in the curly braces is the noise times itself, except, well, it's the noise time, the conjugated and shifted version of the noise, of the same noise. And we're going to look at kind of the average value in some sense, which is we're going to integrate over all time. We can't divide by the duration, because that duration is infinite. Now, that doesn't get us very far. So what we can do next is to use the fact that the autocorrelation is even symmetric. So we can look at the autocorrelation of minus tau. And now what pops out of this is convolution. So now we look at the expected value, again, of what's inside. Now what's inside is changed because we're looking at minus tau instead of plus tau as the argument for the autocorrelation. We end up with the same integration over all time, an averaging effect over all time. And now it looks like convolution. So we basically hold a signal in place, n of t, and we flip and slide another signal about it. And to make it work, to make it work in convolution, we have to, in the convolution argument, flip the time axis. And it all works out. So again, we hold one signal in place in autocorrelation. We hold the signal in place, and we slide the same signal across instead of flip and slide. That's correlation. To make convolution behave the same way, we have to flip the second argument so that when it goes through the convolution formula, it gets flipped back to where it was, and we end up with just a slide instead of flip and slide. Okay, so that is the good news here is that these two are equal because of symmetry. Rn of minus tau is equal to Rn of tau, and we now have a convolution effect to compute autocorrelation, and then to get the power spectrum, we take the Fourier transform. Okay, so let's go ahead and have this play out for the Gaussian random process. So we start in our earlier discussion, our noise in the background noise, thermal noise in the system. Good model for this is Gaussian random process with zero mean and variance sigma squared. So the next thing is, well, what's the autocorrelation if I have a noise signal multiplied by a shifted version of the same noise signal? And if you step back and think about this just intuitively for a second, the noise signal is zero mean, which means that it's equally likely to be positive in value as negative in value. So n of t is equally likely to be positive in value or negative in value. N star of t plus tau is equally likely to be positive in value, negative in value. If I multiply two negative numbers, I get a positive. Negative times a positive, I get a negative. Two negatives is a positive. Two positives is a negative. So if that was easy to follow. So 50% of the time, n of t is positive. So n of t can be positive or negative. And star of t, t plus tau, same thing, half the time. So this is 50% case. Well, 50%. There's always a chance of 0. So equally likely. I guess we'll do the third case in here. So if n of t is positive, and n star of t is positive, then the result's positive. If n star of t plus tau is negative, then the result's negative. And if n star of t plus tau is 0, the result is 0, right? So this gives either greater than 0, less than 0, equal to 0. I do this one, and I'm equally likely here. So the result of the product, again, I'm equally likely to be negative as positive in the product. Do the second case where n of t is less than 0, then the product so if I'm less than 0 and I multiply by greater than 0, I get less than 0. If I'm less than 0, multiply by less than 0, I'm greater than 0. If I multiply by less than 0 and something that's equal to 0, I get 0. The point, and if I multiply by 0, then everything's 0. Right, so that product is all 0. But what the takeaway here is that, again, the product of a noise multiplied by a shifted version of the same noise for any point in time. So pick a point in time little t. They're independent statistically, sample to sample in this process. So I'm equally likely, this product is equally likely to be negative as it is positive. And I have some probability to be 0. Infinitesimal, perhaps. But so the expected value of this product, when tau is not 0, is 0. The average value is 0 when tau is not 0. When tau is 0, they're perfectly aligned. Tau is 0, they're perfectly aligned. So now the expected value, essentially now I'm looking at, when tau is 0, I'm really looking at little n of t times n conjugate of t, which is the same as well, yeah, we're doing autocorrelation, but inside the argument, n of t times its conjugate is the same as absolute power, absolute value squared. So it can't be 0 anymore. So we see it as a spike. So when tau is 0, all the variance piles into that point, and we get an impulsive autocorrelation. And when tau, so in other words, when tau is not 0, this autocorrelation function is 0. When tau is 0, the autocorrelation function is a Dirac delta, continuous impulse. And the Fourier transform of that impulse is the Fourier transform of the Dirac delta. It just gives us a constant in frequency. So this gives us a flat power spectrum for a Gaussian random noise process, 0 mean. Infinite duration observation. Okay, so we don't have the luxury in practice to do infinite observations. It's for bound. So we can do in practice. So what we've been doing, generate some noise. Here I generate 16,384 samples. I generate that many random numbers following the Gaussian distribution, 0 mean, variance 1, using the rand(n) function in MATLAB. And then I just plot the absolute value of the FFT squared. I just directly plot the magnitude squared because I can't, because it's finite duration. I don't have to worry about, the Fourier transform exists. I don't have to worry about it not existing. It's a finite number of samples. Each has a finite amplitude. So I'm good. So in practice, we don't have to worry about all this. All this theory is very nice for deriving bounds, which we'll show to get the match filter implementation or the match filter equation. But in practice, we don't need to worry about any of this. What we will see in practice is noise that isn't flat. It's going to wiggle around. And we can approximate it. You could eyeball it if you wanted to. You could approximate the noise floor from the plot of the power spectrum, which is going to wiggle around over frequency. It won't be flat. We need an infinite amount of time, which we don't have luxury in practice. But if we had, then we would get a flat power spectrum in theory. And that flat power spectrum would have a value of sigma squared. In practice, we'd have to approximate what that variance is, given a power spectrum plot. All right, so that is okay, so that's our aside for the autocorrelation and power spectrum. And now there are a couple of interesting things we can now do from a signal processing point of view to get our hands on, finally, formulas for both the average noise power and the instantaneous signal power. And we can plug those back in to get our match filter derivation, or match filter formula. And this slide will probably take us to the rest of the time, so let's go through it. So again, we had the same setup, pulse shape, match filter, additive noise in the channel. So the noise that comes through is the WT, the noise in the channel, involved with the match filter. If the noise had a Fourier transform, then we could simply say that the Fourier transform of the noise is just the product of the Fourier transforms. The problem is that the Gaussian random signal here doesn't have a Fourier transform. It's the bad news. But it has a power spectrum. So we can do the same, apply the same idea for power spectrum, which is the power spectrum of this filtered noise is the power spectrum of the noise that's input into the filter and the magnitude response squared of the match filter. So we can multiply in this power spectral domain. And so what we get out of this is the variance, that's the variance of the noise, times the magnitude response squared of the filter, of the match filter, which we haven't defined yet, but we're going to just have it as a placeholder. And then the average noise power we can compute either in the time domain or the frequency domain. So we use Parseval's theorem. We've talked about this before. So I can do the calculation either in the time or the Fourier domain, which is ever easier. And in this case, it's going to be easier in the Fourier domain. Okay, so we can either integrate over all time n squared, or we can integrate over all frequency against the power spectrum. So we end up with this formula that gives us now the average noise power as a function of the match filter that we're going to design. On the signal side, on the pulse that gets through the match filter and the sampling block, we have G naught involved with G of t, the pulse shape, and the impulse response. Now we can use the more familiar Fourier transform property involved in the time domain multiply in the Fourier domain. If I want to go back to the time domain, which I do need to do, because I have a sampling operation to follow, is I just simply take the inverse FFT. So here's the inverse Fourier transform of G naught of F. So this is just the inverse Fourier transform. And then I want, in particular, the value in little t is capital tau. And to get instantaneous power, I take the magnitude squared. So now I have the, okay, I'll do one more slide then. Take this inverse Fourier transform, replace little t with capital T. and then take the absolute value squared of both sides. Now I have a relationship between the signal power that gets through the sampling block as a function of the match filter, and I have an expression for the average power as a function of the match filter. Right? Our goal is to find the match filter. All right, so let's go ahead and get there. So what we want to do is find almost finished here for the derivation. One more slide after this. I want to find the impulse response that maximizes the peak pulse SNR. I don't know what it is, although I told you what it is. Right, but right now we don't know what it is. All right, so I have now, if I take the previous slide's results and put them into the formula for peak pulse SNR, I now have, it looks pretty messy, but it'll get better in a second. I have the I have the match filter showing up in numerator and denominator, which I don't know yet. What I do know is everything else. I know the pulse shape and its Fourier transform. So this is known. And I know what T is, that's known. And I know what this is just sigma squared, that's known. So the only unknown I have really in all of this is the match filter, impulse response, or equivalently its Fourier transform. So now I'm going to go ahead and get it out of there. Trying to get rid of it for a second. We'll see how to do that. All right, so so this is what it is. We'd like to bound this. We'd like to know how much SNR can we support, and this formula will be very useful in simulations later. How do I bound this? Well, it turns out I can bound this by thinking about this problem in terms of vectors. So think back to vectors for a second. I have two vectors, A and B, and there's an angle between them, theta. And if I take the inner product of the two vectors, there's an inequality, Schwarz's inequality, that helps us figure out what that is, how to relate either we can bound the inner product, and we can also use it to find the exact angle between the two vectors. Right? So this angle between the two vectors is the inner product of the two divided by their norms, their lengths. The maximum value occurs when? For what value of theta do we get the max? We reach the bound here. What value of theta? Theta. What value of theta do we get? So what value of theta? 0. Right. So when the two vectors are parallel, we get we hit the bound. Okay. Now to make it more interesting, there's a notion of inner products that are related to functions. And we can say that the inner product of two, this is maybe a little bit new, but you can describe an inner product of two functions as the integration of their product, but I have to conjugate phi 2 just in case it's complex valued, which could happen if especially if we're in the Fourier domain. So it turns out we can replace the same notion of inner products with this notion of an inner product of two functions. So here I have essentially the absolute value squared of the inner product of two functions. So this is so this is the absolute value squared as less than the inner product on itself, phi 1, and the inner product on itself, phi 2, which is the same as the above formula here. So this is just the same idea for functions. And the upper bound is reached if the two functions are parallel, and the way that you define it is just the way you define it with vectors. That phi 1 of x would be a real valued, a scaling of phi 2 of x. They're going to be parallel. Hang in there. This is the most theoretical lecture we have for the semester. Just hang in there for just less than a minute. All right, so the good news is if we let phi 1 equal h of f, again, which is what we're trying to figure out, phi 2 equal what we know, which is the Fourier transform of the pulse shape, in this case conjugated, times e to the minus 2 pi f tau. We know, capital T, we know T, this is the symbol time. then we can use this relationship from the previous slide to bound the signal-to-noise ratio. And this bound no longer involves the match filter, which is nice. So now we have a bound on the maximum value that the SNR can obtain, and it's simply a function of 2 over n naught, this is the same as 1 over sigma squared, times the energy in the pulse shape. And the energy in the pulse shape is calculated in the Fourier domain, so it's the integral over all frequencies of the power spectrum. So this is the energy in the pulse shape. We know this bound now. Right? Given a variance of the noise in the channel and a pulse shape, we can compute the max SNR we can reach. We also know when that max SNR is reached. That max SNR is reached when phi1 is equal to k phi2. And phi1 is simply what we're looking for, which is h of f. So it tells us that when h of f is equal to a scaled version of phi2 of f, we've hit the bound. That tells us that the best match filter we can ever come up with to maximize this measure of SNR is simply k times phi2. And if we do the inverse Fourier transform of that, we end up with what I started with, which is just the optimum value of the impulse response of the match filter is a gain times a conjugated, flipped, and slid pulse shape. So that was a long derivation to get to a very simple formula. Okay, but along the way, we got autocorrelation. K is a constant multiplier, and it can be any constant, and it turns out even 0 satisfies the optimization criteria, but makes for a terrible filter because nothing's getting through. All right, so we don't want. So K is real value is a constant. Okay, we'll pick up on next slide when we come back on Wednesday.